So how can we connect momentum to an even earlier topic, the topic of projectile motion? Okay, so here's our projectile. Okay, you shoot that across the lab room, and I want to ask, is momentum conserved for the projectile? All right. Well, we know from our earlier projectile motion chapter, right, as this thing is going across the room, the only force that acts on it is gravity. Okay. Well, here's Newton's second law in the x direction. So net force equal time rate of change of momentum in the x direction. Well, in the above picture, you only have a vertical gravitational force, so the net force in the x direction is 0. So if there's a 0 there, that means that, whoops, dpx is 0. So that means that the momentum in the x direction is constant. Okay, but remember, momentum is mv. So that says that mvx is constant. Divide by m, so constant divided by m is still another constant. So that says the velocity in the x direction is constant. Okay, so using the concept of momentum, we get something that we knew from the projectile motion chapter, that there's nothing that can change the x component of the velocity. So momentum's conserved in the x direction. If I look in the y direction, okay, Newton's second law in the y direction says the only way that the momentum in the y direction can change is if there's a net force on it. Well, there is a net force in the y direction. It's minus mg. That points downward. So minus mg is time rate of change of momentum in the y direction. Okay, so that says momentum's not conserved because there's a force in the y direction that changes that. And we already know, right? Because this component Vy starts like that, shrinks to 0 at the top, and then it starts looking like that later. So the momentum in the y direction points up when it starts, momentum in the y direction 0 up here, and then the momentum in the y direction points downward over there. So if I put in my net force as minus mg, whoops, minus mg, and momentum in the y direction is mvy, masses drop out, okay, I get minus g is equal to, this thing here is dvy dt, and the time rate of change of the velocity in the y direction is the acceleration in the y direction. And so we get something that we already knew, that the acceleration in the y direction is minus g. So for projectile motion, momentum is conserved in the x direction, but it's not conserved, it's not conserved in the y direction, which we already knew that. All right, so if you can find circumstances for when momentum's conserved, it's use the bookkeeping tool. So pretty much we use momentum to analyze collisions. All right. So now for collision, I put contact is not necessary, and I'll show you some demos where I have carts. Okay, they have little magnets on them, so they can interact where they don't physically have to touch. All right. Same as like when a planet goes near another planet. Okay, you can think of that as an interaction of forces. You definitely don't necessarily have contact. All right, so I want to look at two objects in a closed and isolated system. Okay, all this means is I only have two objects. There's no number 3. Okay, and just think of these things as going through the air. They don't have to be air hockey pucks on a table or ball on a table. Just two things, and they're heading toward each other. So I made M1 small. I made M2 big. I made M1 going slow. I made number 2 going fast. So this is my before picture. This is my during picture. Okay, so when they collide, they exert forces on each other. And then the after picture, because I made number 2 large and moving fast, they're going to be both moving off to the left. Okay. Now, if I look at the collision forces here, okay, which of those collision forces is larger? Well, Newton's third law says that they're equal and opposite. Okay, there's no way that M1 can exert a force on M2 any differently than M2 exerts a force back on M1. So these two forces are equal and opposite. So what I want to do is I want to calculate the change of momentum for each object. So I'm starting with Newton's second law, and I want to find delta P. So I'm going to start with this, multiply both sides by dt. Little dt there, little dt there. Okay, so that would cancel. So I have dp is my net force dt. Integrate both sides. Okay, integrate both sides. All right. Now I want to find delta p. So I integrate both sides, and I get delta p. So if I do this for number 1, okay, whoops, for object number 1, I integrate that, and I get delta P1. And the net force on number 1 is that one. This is the force on 1 due to number 2. So that's a change of momentum of number 1. If I do this integral here for number 2, okay, for number 2, integrate dp, I get delta p, and the force, the external force on number 2 is that. This is the force on 2 due to number 1. Okay, so I had the change momentum for 1 and change momentum for object number 2. So I rewrote the change momentum for number 1. Okay, but this force in here, F12, is equal in magnitude but opposite in direction as F21. So right here I said F12 is minus F21. So in here I put minus F21. Brought the minus sign on the outside, but this integral right here is just delta P2. Whoops, little arrow there. Okay, so this integral here is just that integral right there. So here's my minus sign. So I have delta P1 is equal to minus that integral, which is delta P2. And that's what I wrote there. Okay, so for example, if number 1, okay, if the change of momentum of number 1 is 3, okay, then the change in momentum of number 2 would have to be minus 3, because I have 3 on the left, I have to have a 3 on the right. Okay, so they're equal and opposites. So in magnitude, that's what this says. They're equal and opposite. Okay, they're equal in magnitude. Vector says opposite in direction. Okay, so I took minus delta P2, whoops, and I brought it over on this side, right there. So I brought P2 over, all right? And then I'm going to call the total momentum P1 plus P2, right? So here you can think of I'm factoring out a delta. So delta P1 plus delta P2 is my change in P1 plus P2. So this is what we're calling the total momentum. Okay, so that says for that collision, the total momentum change is 0. Total momentum doesn't change. If it doesn't change, that means the total momentum is constant. Okay, so for a collision, right, again, as long as there's no hand holding on to one of these, okay, for a collision, we show that the total momentum is conserved. So P initial total equal P initial final. So as long as there's no net external forces, okay, for example, these things couldn't be colliding on a rough surface, okay, there has to be no external friction force. So for collisions, momentum's conserved. So it doesn't matter that this one's moving slow and that one's moving fast and they're larger, okay? The change of momentum is equal and opposite, the collision forces are the same, and momentum is conserved for the system.